electromagnetic field in the Coulomb gauge. So, and we have these conditions, etc., so that the divergence of this operator is 0. And let us see, there was something I wanted to say. Okay, so this is often written as, it's useful to think of this as the sum of two parts so this is a plus, this is not a dagger, this is a plus, and here there's a minus. So these are called the, so this first part that contained only the annihilation operator. So if you just take away the second part of the sum, if you just have this part, this is called A plus, and this piece with, many this contains only creation operators, and this is referred to as the positive frequency, part, and this is the negative frequency part. So it's just conventional to think of, so this part here that has an e to the minus I omega t, you're used to in non-relativistic quantum mechanics, an energy eigenstate that has a time dependence e to the minus I et, when that has a energy E, so it's just conventional to think of this as a positive frequency. So positive frequency and e to the I omega t, so we call it a negative frequency. Now the important thing is that it is often useful in calculations to split the field into parts that have annihilation operators and parts that have creation operators, especially later when we do interacting field theory and so on. We'll find that it's useful to do that. All right, so we're going to look now at the electric dipole interaction. So it could be an atom interacting with the electromagnetic field. So, we talked a bit about this earlier. To discuss the interaction, imagine here you have an atom and it is interacting with this quantized electromagnetic field that we have over here, there is an interaction Hamiltonian that describes that. Now, we're working in the Heisenberg picture. So the electromagnetic field, we have the electromagnetic Hamiltonian, which evolves the field operators. Okay, this field operator is time dependent. We're in the Heisenberg picture, and field operators evolve according to the Hamiltonian of the system, and the state is static. And one would do a similar thing here, even though we won't need it explicitly. This would evolve the atomic operators. So imagine for a moment there's no interaction, and we just have two separate systems: the atom with its Hamiltonian, the electromagnetic field with its Hamiltonian, and we're in the Heisenberg picture. So the state is static, and the operators evolve according to the Hamiltonians. Now, what we're going to do is, I'm not going to discuss this very explicitly because we're going to do it properly later on, but when we include the interaction Hamiltonian, we're going to work in the interaction picture where the state psi evolves via the interaction Hamiltonian only. Now, you should have seen the interaction picture before. We're going to do it more explicitly later on because we're not going to need to know much about this. We're just going to use a result from standard perturbation theory that you've done. But anyway, just so you understand what's going on, the state evolves via the interaction Hamiltonian, and the rest of the Hamiltonian, i.e. H atom plus H plus the atomic Hamiltonian plus the electromagnetic Hamiltonian, this makes the operators evolve. So the nice thing about this is that even though now there is the interaction, let us say what's nice about this. The result of this is that everything we have done for the EM field stays the same. Stays the same. So remember, in the interaction picture, the electromagnetic field is now interacting with an atom. We have an interaction Hamiltonian. The field operators still evolve according to the electromagnetic Hamiltonian. So all of this is exactly the same. This is the field operator evolving according to electromagnetic Hamiltonian. That stays exactly the same. The only change is this thing. So the only change is that the state psi now evolves according to the Schrödinger equation, but involving the interaction Hamiltonian only. All right, that's the only change. So, what we're going to be interested in particular is, so for example, so e.g., if at time 0 we have a state let us say we have an atom. We may as well use the notation we're going to be using. All right, let's do that. So you can write this if you want to be you can write this as a cross product. So I have an atomic state. So I have an initial atomic state. A might be some energy level, and we have the initial state of the electromagnetic field where you have NKR photons in the mode KR. And it's understood that there's, well, let's assume that there are no photons in the other modes, but you don't have to. So this can evolve over time into a state at time t that is equal to cross NKR plus or minus 1. So here we have a final atomic state. And here we see that the electromagnetic field has gained or lost 1 photon in the mode KR. So if there's a plus sign, plus sign, the atom has emitted a photon. With the minus sign, the atom has absorbed a photon. All right, so what I'm going to describe to you, so the atom is a complicated object which contains various charges. There is an approximation which we're going to study, which gives us a useful model which allows us to, it's a kind of simple model that allows you to see for the first time exactly how these processes occur, how to describe them in quantum field theory. But it is also a very good approximation. The electric dipole interaction is valid when the wavelength of the photon, so the wavelength lambda of the photon is much bigger than the size of the atom. So for example, optical transitions, you might have lambda, let's say 5 or 6,000, say maybe, okay, let me put a range here, 4,000 to 7,500 angstroms, okay, the optical region. So you have an atom emitting or absorbing a photon of this wavelength, and of course the size of the atom order just 1 angstrom. Okay, so this is fine. This is a good approximation. In fact, this is used a lot in quantum optics. Now there is a more detailed theory where you consider the various charges inside the atom interacting with the electromagnetic field. It's a theory that's described later in the first chapter of the book. Basically what you're doing is you're treating the electrons as a non-relativistic system using the quantum mechanics and the Hamiltonian that you're used to, and you let it interact with the electromagnetic field. It's a theory that is it's sometimes called non-relativistic electrodynamics. So you've got non-relativistic matter interacting with the electromagnetic field. We're not going to go through that because we're interested more in high energy physics. We're going to be looking at relativistic electrons and positrons, high energy electrons and positrons interacting with the electromagnetic field. But there is an approximate theory that works at low energies when the atoms or the electrons are slowly moving and the energies are non-relativistic. There is a theory that you can use from which you can derive this approximation. But we're not going to go into it because it's something that's used again more in atomic physics, quantum optics. This course we're more focused on the high energy domain. So I'm just going to study, but this approximation is very nice because it gives you a quick insight in a simple way into how quantum field theory works. So here is the conditions. Okay, approximation is valid. Also, sorry, there's one other assumption. You are neglecting the interaction with the magnetic field B. So it's only the electric field that is important. All right, so the interaction is the following. Is equal to minus the dipole moment of the system, its dot product with the electric field operator, where the electric field operator, let's take the electric field operator is evaluated at the origin, where the atom is located at R is 0, the origin. So what's happening here is we have the atom is located at the origin. The wavelength of light of the photon that's being emitted or absorbed, let's say this is some region, spatial dimensions R. Lambda is much bigger than R. In these conditions, you can neglect the spatial variation of the electric field operator. I'm not going to go, if you want to see this justified, if you're interested, you can have a look at the theory, as I said, of non-relativistic, a system of non-relativistic electrons interacting with the electromagnetic field, and you can show that in these conditions this works. But we're just going to take this as a valid approximation. So now you know, of course, that the electric field operator, I've been using, why is he suddenly switched? I see, okay. All right. Let me put X's there. I'm using X for vector positions. So the electric field operator is of course given by minus the time derivative of the vector potential operator. And the dipole moment, so we have an atomic system that has, let's say we have an atom with n charges, E1, E2, En, with position operators. So let's call them R1, R2, Rn. So X is a general position, the point in space, and the R1, R2, Rn are the positions of our n charges, and the dipole moment operator is defined to be. So it's just the sum over the charges times their positions. So something you should have met when you did electrodynamics, definition of the dipole moment. Of course, this is an operator. So this is the dipole moment operator. And our interaction Hamiltonian, as I've written there, is taken to be minus d dot E, where E is evaluated at the origin where the charges are located. Okay. All right, so this is the approximation we're going to work in. And for our purposes, this is what physicists sometimes like to call a toy model. A toy model of a system interacting with the electromagnetic field. Okay, so it's important that you get clear on how this works, because we're going to be doing similar things later, but with more complicated systems where we have two fields interacting. So I've got field modes here, exchanging energy. Here we've got field modes here, and the system here is just a simple system with, let's say, two energy levels. We're just going to consider two energy levels. All right, so let us see. We're going to define one other thing. I'm going to define is let us write this as for our all right, leave that. All right. So we're going to consider an atom. So take all charges EI to equal minus E. Okay. I should have mentioned that. Let us now take for an atom with the nucleus at the origin. If I calculate this sum, then the only terms that contribute are the electrons, which all have charge minus E. So what I'm going to write is let's define, I'm going to follow the notation of the book, define a vector x, and it's an operator that is a sum over I of the position operators for the electron in the atom. So this is just a sum over the atomic electrons and we're going to call this x, not to be confused with the general position in space, the general point in space. All right, so we have P. Our operator is written now like this, minus E times an operator x, which is a sum of the operator positions of the atomic electron. So this is the dipole moment operator that we're going to work with. And now we need to work out what is the electric field operator at the origin. What is the electric field operator at the origin? So, that's easy enough. So that's just to make sure we understand exactly what we're doing. Let's write out the expression for the electromagnetic field operator, the vector potential. That is our expression. Have I done that right? I've done that right. That's our vector potential operator. The electric field operator at a general position is just minus the time derivative of this operator. So what is that? I bring down the minus I omega. And here I bring down the plus I omega. And now we have to just put in, so this is the electric field operator, the general point in space. Let us now put in x is 0. Again, let's not confuse x, which is a position of the general point in space, with this x that's been introduced here. All right, so at the origin, what's the electric field operator? At the origin, well, we're just going to put in x is 0. And so what do we get? The electric field operator, I can bring out a factor I. I can write it like this, I times the sum over kr. I've also got an extra omega. Here there's a 1 over root omega. So, I have a root omega at the top. So I can write it like this. I've got the square root of omega over 2v epsilon kr a kr e to the minus I omega t minus a hat dagger kr e to the I omega t. All right, is that right? So I brought out a factor I. Hang on, why is that? Oh, and of course, remember there's an And of course I forgot to, when I took the time derivative, there's an overall minus sign here, which I forgot to put in. There's a minus. Someone should correct me when I make these mistakes. Anyway, there's a minus. So here's why I get a minus, so I get to take out an I, so I get a plus a hat e to the minus I omega t minus a hat dagger e to the plus I omega t and the omega root. Okay, that looks right. All right, so this is the electric field operator at the origin. That's the part that we really need. And remember, our interaction Hamiltonian is minus d hat dot e at the origin, so it is equal to e x hat dot e. All right. So let us consider the emission of a photon. So we're looking at a transition from A, so instead of writing it as a cross product, I can just write the state like this. It's a state, it's a cross product. There's an atomic state. There's an atomic state and the electromagnetic field state. Write it like that. That's the initial state to a final state, which is, we're going to call the atomic state B, and the electromagnetic field has gained a photon. All right, so the atomic state has changed from A to B, and the photon has been emitted. To use this heuristic language, a photon has been emitted. So we need to consider the transition matrix element. As we'll see in a moment, the probability, and it's something you've seen before anyway, but the probability of this transition is related to the following matrix element. You have to work out the matrix element of the interaction Hamiltonian between these two states. Now remember, our quantum state is evolving according to this interaction Hamiltonian. And if you treat this interaction as small, and you look at first order perturbation theory, then it's something that you should have done before. So time-dependent perturbation theory So treating this interaction as small perturbation and working out, okay, the lowest order, what is the change in the state, and you should be familiar with this expression, which I don't know if people still call it this, it used to be called Fermi's golden rule. So, which says that the transition probability per unit time is given by, so the transition transition probability per unit time is given by this formula. I'm going to put in an H bar. These are probably more familiar with it written like this, just to recall forgotten memories. So you look at the transition matrix element. So here, this is the transition matrix element between the initial and the final state, and you take the modulus squared, and there's a 2 pi over h bar, and there's an energy conserving delta function. So energy conservation just says that the initial energy of the atom is equal to the final energy of the atom plus the energy of the emitted photon. Now, I'm not going to go into the derivation of this and all these things that you've done before. There's another reason, is that we're not going to use this again. We're going to look at this simple model as a nice way of understanding how photons are emitted and absorbed. But later, when we do the formal theory, we're going to be looking at the interaction of high energy systems. And we're going to re-derive the perturbation theory in a form that is valid. For general field systems, we're going to have fields interacting with each other, and so we're going to look in the fields interacting in the interaction picture, and we're going to derive a series expansion for perturbative interactions that we're going to be using. So this is just a one-off appearance of an old friend in this context, which is just a quick and easy way of looking at this example. So, all right, so to calculate the transition probability per second, we need to work out this matrix element between the initial and final states. So, how do we do that? Let's have a look. All right, so here is homework problem. So check that this matrix element, so B NKR plus 1, the matrix element with the interaction Hamiltonian, where the interaction Hamiltonian is minus D dot E at the origin. And this is given by I times the square root. Let's put in some H bars. We're going to put in H bars here. There's an H bar omega here. Over 2V. Now, what you have to think about here is that NV, this operator acts on the atomic part of the state, while E hat and of course A hat dagger act on the electromagnetic part of the state. So this comes out to be NKR plus 1 A hat dagger KR NKR times B epsilon KR dotted times e to the I omega t. Now let me just go over. So please go through that and check that's the case. But just to make sure you know what's going on. So this is the first time you're going to be later on in this course, you're going to be calculating transition matrix elements. You know, it's going to become like pouring milk on your cornflakes. It's going to be something you're going to be doing a lot. So you have to get used to this. So, but this thing is, this is the first time you do this. So, first of all, it's probably a good idea, seeing as we've got a particular mode, we're talking about a particular mode Kr, which has n photons and then nkr, n plus 1 photons. We don't want to confuse the k here. There's a particular mode. There's a particular mode Kr. You don't want to confuse that with the sum over modes here. So maybe let's put a prime here on all of these k's and r's and omegas. Let's put a prime. And if you look at the transition matrix element, so we have B, this is equal to B plus 1. We have an interaction Hamiltonian minus D dot E. Now, if you look at this, all right, let's take out the minus sign. So I'm getting you started on your homework here. We have D dot. What is this? I'm taking out the minus sign. I'm looking at D dot E. What I could do is I could bring in the D. I could write it like this. Sum over I, sum over K prime R prime. That should be, let me put, I'm putting in H bar, so there's an H bar in here. So where is H bar omega prime divided by 2V. Now let's bring in that D dot. So D is a vector, it's a vector operator. And of course here this is a vector. So I can write this as D dot epsilon KR. If I make a mistake, please tell me. Minus A hat dagger K prime R prime e to the I omega prime T. So have I done this right? I've got the minus outside, I've got D dot E. So I've got I sum of K prime, blah, 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 D dot epsilon, and the rest is the same. All right, so this is a sum over all possible modes, and it reduces to a single term. Now, why is that? Well, okay, so here is where you can go through it step by step if you like, but if you think about this, there are terms of the form. There are terms with B. Let's look at the terms involving the annihilation operators. So remember, the creation and annihilation operators act on the electromagnetic part, and the D operator acts on the atomic part. Okay? So now let's think about terms involving, just thinking about the electromagnetic part. I have the annihilation operator for a general mode, and it's sandwiched between nkr plus 1 and nk. What is this going to equal? Remember, the annihilation operator lowers the occupation number. Now, there may or may not be photons present in the other modes. Let's assume there are no other photons present. So the mode Kr has n photons, the other modes have no photons. Let's imagine, let's take if, just, I mean, it's pretty obvious, but let's just go through it slowly because it's the first time. Imagine if k prime r prime was equal to kr. Remember, there's a sum over all the modes here. Well, then in that case, what you would have, this would be the inner product of nkr plus 1 with nkr minus 1, which is 0. All right, here I've lowered the occupation number, so I've got an inner product between a state with n minus 1 photons and a state with n plus 1 photons. They're orthogonal states. So this will be 0. If instead k prime r prime is not kr, well, if there are no other photons present in the other modes, then you have the ground state for the other modes. You act on it with the annihilation operator. You annihilate the state. So again, it's 0. So again, it's 0. So what does that tell you? So it tells you that all of these terms are 0. All right, there's no contribution from those terms. If we now look at the creation operator, the terms in the creation operator, terms in nkr plus 1, and the creation operator. So what happens? So if k prime r prime is unequal to kr, so once you get used to this, you would just write this down. But the first time, let's just go through very slowly. If k prime r prime is unequal to kr, what's going to happen? You would have a state. You would be taking the inner product of this. Here you would have nkr photons in the mode kr, but you would also have a state, a photon in the mode k prime r prime. Okay, here you create a photon in the k prime r prime mode. So this is proportional to this state. So now I have an inner product of two states. There's one state where there are nkr photons in the kr mode. There's one photon in the k prime r prime mode. I'm taking the inner product with the state where there are n plus 1 photons in kr and no photons in k prime r. Obviously, this is 0 again. So this is 0. I think everything's 0 here. No, not everything is 0. So if instead, here's where finally something happens. If k prime r prime is equal to kr, then what do we have? Then we're going to have, if k prime r prime is equal to kr, so let me get rid of the primes here, this is going to equal the square root of nkr plus 1 times the state nkr plus 1. All right, I just raised the occupation number by 1 in the kr mode. So nkr becomes nkr plus 1, and there's an overall factor. And of course, now the inner product of nkr plus 1 with nkr plus 1 is 1. And so this inner product is now the square root of nkr plus 1. So in fact, what I can do is I can write this result. So I can write this result as follows, is I times the square root of h bar omega over 2v times nk, let's write the square root of nkr plus 1 times the matrix element for the atomic part. A times a factor e to the I omega t. So you see that this sum, you've got an infinite sum of all the different modes. All of the terms in the annihilation operators give no contribution. Summing over all the terms in the creation operators, there's only one term that contributes to this transition. And of course, then there's still the matrix element for the atomic part. And so here we have, there's the dipole moment operator acts on the atomic part, and it has its dot product with these little vectors, and so I have this term here, this is the atomic part. Okay, this is our result, so please check. Please go through that, please check, make sure you understand exactly where that came from, because we're going to be doing similar things later, but with more complicated cases, and importantly get used to. And of course, normally, you don't want to have to laboriously go through it. You want to be able to sort of quickly see, oh, okay, look, this is the only term that's going to be non-zero. It's straightforward, really. But of course, if you've never done it before, then you need a bit of practice. All right, so we have our transition matrix element. This is our transition matrix element from the initial to the final state, and now we need to plug it into remember the probability per unit time, or the probability, right, it was transition. So just taking over this result from time-dependent perturbation theory, we're going to need this modulus squared of the transition matrix element with the delta function here. All right, now here's something that let me just introduce also as a notation, define omega AB to be EA minus EB over H bar. So there's a particular frequency, of course, that is allowed by energy conservation. So omega is our general frequency, this is the allowed frequency. Anyway, something again that you should have seen, so we have an atom, remember we have our atom localized at the origin, and it is in this heuristic language, it's emitting a photon with wave vector k and polarization r. Now, what we do, there's something that you should have seen this before. How do you get rid of this delta function? Is you integrate over a narrow range of final states. formally the transition probability per second for the atom to emit the photon with one definite wave vector. But what you do is you consider a range of wave vectors. So over some, you might consider, let me write the wave vector, or actual vector. And you might consider some range of wave vectors, some little element d3k. So imagine I've got some little volume element in k space in a volume d3k. So imagine I'm in k space and I say, well, I'm not just considering one particular vector, I'm considering a little range of vectors. A little range of vectors, slightly different directions and magnitudes. And what we do is we say that, well, the probability per second for a transition into this range, probability per second for a transition not just to one value of k, but to any value of k in this range, is equal to W times the number of k vectors in this range. Now remember, k is restricted to be we wrote it, but was it nx or was it n1? I think we called it n1, n2, and n3. Anyway, there's a triplet of integers times 2 pi over L, where V is L cubed. And you might ask, what is the our result for, let's just write final, the transition matrix element from the initial to the final state. Let's keep that there. So something again that you should have known before. So the number of k states, if you want to call it that, in the volume element d3k is equal to v d3k over 2 pi cubed. So if you don't know that already, if you think about it, remember there is really a lattice, a discrete, in k space, there's really a discrete lattice of allowed wave vectors where these are integers going 0, plus or minus 1, plus or minus 2. Another way to think about it is, remember, we've already said that there's a correspondence between summing over k and integrating over k in the limit where the normalization volume becomes very large. So where there's a 1 over v sum over k and a 1 over 2 pi cubed times the integral, or equivalently a sum over k corresponds to v over 2 pi cubed integral d3k. So you can see what it must be if I'm just summing over k in some small volume. I say how many k's are there in the small volume? Well, from this it's clear that it has to be v over 2 pi cubed d3k. So, all right. So what do we do? So we write, and now this, we can write as follows. We can write d3k as k squared dk d omega, where d omega is an element of solid angle. So if you like, you can just write d omega as d cos theta times d phi. So here what is happening is the atom is at the origin, there's a certain k vector being emitted, and you can imagine you have a detector with a certain solid angle element d omega. Imagine you have a sphere or a unit sphere, and there's some little area element on the unit sphere. You should have seen all this before, but anyway, so we're considering wave vectors of slightly different magnitude and slightly different directions. The directions are restricted to some solid angle element omega, so the atom is emitting not just into one definite k, but into the small range of k's in the solid angle element, and for a fixed polarization R. So, let us now think, what is the probability then? So we want the probability, whoops. So let's keep that formula there. So, all right, so what is the probability per second? Or the transition probability per second for the transition. So the atom makes a transition from A to B, and the photon is emitted with K in a range d3k and some fixed polarization of the photon R. What is this probability? This is, we can write as follows. It is simply it's given by the integral of V over 2 pi cubed d3k times W with a fixed solid angle element. So we're looking at a range. We want to integrate over this range. So let me just make sure to clarify this. The range d3k. So the magnitude of this wave vector is varying. Though of course, really, it's restricted by this delta function. So omega is kc, putting in the speed of light. But still, we can think of k as varying, and we have a fixed, so within, or the direction is restricted to a range d omega. All right, so we're letting k vary within this range d omega, and so I have to integrate this expression over this little element. So what does that do? I have a fixed d omega, but the magnitude of k is allowed to vary. So I'm going to call this WR d omega. It's the transition probability per second for a certain polarization and for the photon to be emitted into that certain solid angle element. And what is it equal to? So it's just the integral with this factor of w here. So I have the integral of, let's write it out, v over 2 pi cubed k squared dk d omega. In fact, I'm going to take the d omega out because I find it a bit factor out, bring the d omega out in front, otherwise it looks a bit confusing. We're not really integrating over d omega. We're just, we're integrating just over this small range here. So let's just take out the d omega and write it like this. And now, of course, we have our w from this formula. So we have 2 pi over h bar, and the delta function omega times, we want the magnitude squared of our transition matrix element. So we want the magnitude squared. Remember before we worked out the transition matrix element, we take the magnitude squared, and what do we find? We have h bar omega over 2v. We have nkr plus 1. And we have the magnitude squared of this atomic part. Sorry, hang on, let's go on a new line. Times the magnitude squared of the atomic part of the transition matrix element. So epsilon kr dot d in product with A magnitude squared. All right. Are there any questions so far here? Everything, I haven't messed up anything, left out anything. Okay. So now what happens? Perform the integral dk. And remember that k is omega over c, so there's a factor c coming in. You've got a delta function, there's an h bar, omega is kc. You can figure this out, I'm sure. And use, let's write d, our d operator. Remember we introduced that abbreviation minus ex. This x operator is the sum over the position operators for the atomic electrons. So, homework, please check this. Go through it. I mean, it's simple enough, but the delta function in there is a function of omega, but omega is kc. There's also the h bar. You just have to, you know how to work with delta functions. So you should find, so homework, check. So please check this. So there are two reasons why you should check this. One is to make sure you understand it, because you want to gain deep insights into the nature of reality and all that good stuff. The other reason to do this is because there might be a similar problem on the exam. You never know, something like this. We have to work out something like this. So please go through it and check that you should be able to find omega r d omega is equal to e squared omega AB cubed. Now remember I introduced, okay, let's write it down again. Omega AB is EA minus EB over H bar. So we've got omega AB cubed, and d omega, and we have 8 pi squared h bar c cubed, and there is nkr plus 1, and we have the magnitude squared of epsilon kr dot x dA squared, where we have defined xBA is defined to be the matrix element between the initial and final atomic states of this quantity x. In other words, just to remind you, x was defined to be this sum over the position operators of the atoms. Let me just check I've written this down correctly. E squared omega AB cubed d omega cubed nkr plus 1 BA xBA. All right. Notice a few things to notice. NB. Normalization volume V cancels out, which it should do. When you come to calculate the actual any numbers, something that you could measure. So remember, this is the probability per second for the atom to emit a photon into a little solid angle element, the omega. This is something you could measure. It shouldn't depend on that large but arbitrary volume V that we were using to make our system discrete. So you know so there's a V here at the bottom, there's a V here at the top, they cancel out. So here you're integrating over dk. This delta function makes sure that k is going to equal omega AB over c. And so you see you get an omega squared, and there's already an omega, you get your omega cubed, there's the nr plus 1. Here we've just written d as E. And it's straightforward enough. So, let us see. All right, so we're going to discuss the implications of this next time. This factor here is particularly interesting. This term here, I'll talk about this again. We'll go back to this. But just to show you, so you can get excited about where we are here, is you've probably heard people talk about stimulated emission and spontaneous emission. So what are these terms? So this term here is telling you that, well, even if there were no photons, remember this is the number of photons present initially. If there were no photons present initially, so I have an excited state of the atom, it's in the vacuum, there's still a probability for it to make a transition to a lower state and emit one photon. So it can emit spontaneously. If instead there are already n photons present in that mode, then the probability for emitting into that mode is increased. So stimulated emission, if there are already, it's like these people, you know, if these people who have already got an iPhone, you know, more people want to buy iPhones. There's this thing of, you know, the photons seem to follow each other. If there are already n photons in this state, the probability for the atom to emit into that state is increased. So this term corresponds to stimulated emission, and this is spontaneous emission. And note, remember the puzzle I told you. If I have, you know, an atom in an excited state in the vacuum, you might think, well, it's just going to stay there because it's an isolated system in an energy eigenstate. According to the Schrödinger equation, the phase is just oscillating and it's in a stationary state. But actually, in the vacuum, there is still the electromagnetic field that the atom is interacting with. Even if the electromagnetic field is in the ground state, in a sense, there's still something there that the atom is interacting with, and the atom can make a transition to a lower state, and the energy of one mode of the electromagnetic field can increase. And that is what we call the emission of a photon. In this heuristic language, the atom has emitted a photon. What has really happened is the atom has lost some energy, and one of the modes of the electromagnetic field has gained that energy and is now in its first excited state. So now the atom is in a lower state, and there is a photon present. Anyway, we'll look more at this. We'll carry on Thursday. Are there any questions about that? All right, so please go through it. Make sure you're comfortable with the matrix element, you're comfortable with this result, and all right, see you on Thursday.